We are going to use the Euler's method with step size 0.1 to estimate the value for y of 0.5, where y of x is the function that satisfies the differential equation y prime is equal to y plus xy, and then we also have an initial condition y of 0 is equal to 1. And here are the formulas for the Euler's method. We have the xn formula, which says xn is equal to xn minus 1 plus h, and we also have the yn formula, yn is equal to yn minus 1 plus h times capital F of xn minus 1 comma yn minus 1, and this is good for n is equal to 1, 2, 3, 4, 5, so on, so on, so on. So here's the idea. Sometimes it may be really hard to solve a differential equation, right? And sometimes it's actually not possible to do it either. Well, first we know a point on the curve, y of 0 is equal to 1. That means I have a point 0, 1. And then I'm trying to reach when x is equal to 0.5, I would like to know what's the y value. So I'm starting right here, and I want to end up right here, but I don't know what's the y value when x is equal to 0.5. Unfortunately, I don't know the curve because I didn't solve for this differential equation. But then Euler's method says, instead of solving for the differential equation, well, that's the ideal situation. We may get a curve, right? We don't want to do that. But instead, we're going to break this into, in this case, 5 pieces, because the step size is equal to 0.1. So we are going to take 5 steps. Instead of going from 0 to 0.5 right away, we go from 0 to 0.1 and try to compute the y value here. And then we go to the next step again. We try to compute this y value and then do it right here. And then as you can see, each of this path right here is straight lines. So this is straight line, that's straight line, that's straight line, that's straight line, that's straight line. And of course, if the h value is small, then the approximation will be much more accurate. And this formula is nothing but just like a straight line formula. Here's the idea. If you start off with a line formula, the point slope form of the line, y minus y1 is equal to m times x minus x1, where m is the slope, and then x1 and y1 are the known points, okay, on the graph. First, let me just add y1 on both sides so I can isolate the y. Y is equal to y1 plus, and let me put down this first, which we will have parentheses x minus x1 and then times m. And as you can see, the y1 is the previous known y value, okay, and that's pretty much this right here, the y sub n minus 1. And then x minus x1, that's a change in x value, which that's the h value we have in this formula. And then the m, it's a slope. And guess what? The capital F of xy, that's exactly the slope because that's the differential equation. Y prime tells you the slope. But then this is based on x and the y value, so we must know both of the x value and the y value in order to compute the slope. So this formula is nothing but just equation of a line, but we'll do it in many pieces. Okay, here we go. Run through the formula. First of all, we know our starting x value is at 0, and then we are going to go to the next x value. x1, you can use this formula, or we can just draw a picture. A picture is much quicker, but then if you follow the formula, it says x1 is the previous x value, which is x0, plus h, which is 0.1, and altogether you get 0.1. And that's pretty much what I draw right here. You start with 0, the next x value you have is 0.1. And then likewise for the x2, you started at 0.1 right previously, right? That's the x1 value, and you added h value, that's a change in x. So you get to 0.2. And then likewise for x3, you get 0.3, 0.4, 0.5 for the x3, x4, x5. And we stop it at x5 because all we care about is just y of 0.5. For the y1, we have to use this formula, which says I need to know the previous y value. So I'm looking at this right here, y0 is equal to 1. Okay, so just plug in right here. Plus the h value, which is 0.1, and that's the step size. And then that's pretty much all I have right here. And then capital F of x n minus 1 comma y n minus 1. The capital F is this formula. And I just have to plug in 0 into x, which is right here, and then plugging 1 into the y, which I have the 1 right here, the 1's right here. And I look at this, use a calculator, 1 plus 0.1 times parentheses 1 plus 0 times 1, I get 1.1. Okay. And then for y2, I will have to use x1 and y1. But first, I have to put down 1.1 for the y1 value, the previous y value that we know. And then we add the h value, which is 0.1, and I multiply. I will plug in this right here for the x value, which is this right here. And I'm plugging 1.1 into the y value. I have this and that right there. Do the computation. I get 1.221. For y3, I will put down y2 first, which is 1.221 that we found, right? Plus h, which is 0.1, and I have to plug in this and that into these formulas. So I plug in this 1.221 into this y, so I have this and that, and then 0.2 into this x, which is that right there. Do the computation, we get this 1.3675. And we'll do the same for y4. Put this down first, and then we add 0.1 for the h value, multiply, plugging this and that into the capital F, which is once again the derivative formula. So we get that for y4. And lastly, put this down, right, for the y4 value, so we can get y5. 1.5453, and then plus 0.1 for the h value, open the parentheses. I will have to plug in this and that into the y and x. So 0.4 goes right here, and then 1.5453 goes into these two y's. Use a calculator, I get my answer. And finally, we know because we are at x5, which is 0.5, and we get the y5, which is 1.7616, we must have y of 0.5 being equal to 1.7616 by the Euler's method. And as you can see, the idea is that every time when we move to the right, we go up by a little bit based on the slope. And then you just go up, go up, go up, go up, go up. At the end, even though we don't have a curve, but then this path is a pretty good approximation. At the end, when x is equal to 0.5, we have that. So the final point that we have right here is 0.5, comma 1.7616. Okay, so this is how you do Euler's method.